All right, so last one, we have 6 things attached. So we're talking about AX6. And so example of this is sulfur hexafluoride. And so the way this is going to end up is you're going to have one above, one below, 2 going back into the plane of the board, and then 2 coming out of the plane of the board. And so all of these bond angles, if you think about it, they're all 90 degrees. And the shape of this is called octahedral. So you may be thinking about, why is it called octahedral? There's only 6 things. It's because there's 8 faces. So if you think about, this is 1 face, this is 2 faces, 3 faces, and then in the back 4 faces, and then you have the same thing down on the bottom. You come up with 8 faces, and so octahedral. Here's a picture of that. You can see in this sulfur hexafluoride, in this top right Google image picture, you can see there's 8 faces, and so octahedral. Let's remove all these lone pairs and build up our molecule. So 1, 2, 3, 4, 5, 6. We got octahedral, and you can see all of these atoms are actually the same. All of these bond angles are 90 degrees. You can see you got 4 things in one plane, and then 1 above, 1 below. And so play the game, AX5E, right? Replace one of the atoms with a lone pair, something like bromine pentafluoride, where the bromine has a lone pair. And so you can replace any one of them. Generally, in the drawings, you replace the bottom one, but it doesn't matter. They're all actually the same. And so, right, the electron geometry is still octahedral. And then the molecule geometry is what we call square, because there's a square down here, and then pyramidal, because it kind of forms this pyramid, right? So you can see there is logic and reason behind it. Let's check that out. So replace one of these atoms, put a lone pair, boom, there is your square pyramidal. And then in terms of the bond angle, the lone pair is going to push more than any of these other ones. And so all of these bond angles are going to be less than 90 degrees. Let's take a look at BRF5. The real atom, you can tell they're all less than 90 degrees. Go. Keep playing the game. Replace another atom with a lone pair, AX4E2. Something like xenon tetrafluoride, where the xenon has 2 lone pairs. And since the lone pairs are bigger than the bonds, you're going to want to put the lone pairs on opposite sides. That way, they're as far away as possible. So the way this is generally drawn is like this, where here it looks like these lone pairs are in the plane of the board, but in reality, one is going out of the plane and one is going into the plane. And so electron geometry, still the same. Molecular geometry, now we are square. And since they're on the same plane, square planar. Let's take a look at that. Replace one of our atoms with a lone pair. You see they go on opposite sides. That way the lone pairs are as far apart as possible, and you get square planar. Don't know if they have an example of that. Yep, here it is. Right, square planar. And then if you think about the bond angles, the lone pairs are pushing against each other, and so they just kind of cancel out. So all the bond angles are still 90 degrees. And then you can keep playing the game, AX3, E3. And so now we need to replace 3 of our things with lone pairs. I don't have a shape for you here, unfortunately. So we have A, and we have X, 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 and then lone pair, and then yet another lone pair, right? So still the same electron geometry, but now our shape is T-shaped. So the same shape as before, except the only thing here is that these bond angles are now less than 90 degrees. So let's take a look at that. Take another atom away, put another atom in, and you get T-shaped. But the model obviously doesn't show the less than 90 degrees. And then one more time, AX2, E4. And so we'll just replace another one of it, another lone pair with stuff. So X, X, and then we'll have 1, 2, 2, 3, 4 lone pairs, right? Still the octahedral electron geometry, but now the shape is back to linear. And so this is 180 degrees. Let's take a look at that. Take another atom away, put another lone pair in, and there you go. You have your linear shape. And that's it.